probably heard arguments that free will is an illusion. The Calvinists believe it, based on the sovereignty of God. Way on the other side of the ideological spectrum, Sam Harris believes it. It's quite amazing that Sam Harris and Calvinists can believe the same thing, because Sam Harris is about as atheistic as they come. But Sam Harris believes that free will is an illusion based on causal determinism. That is the idea that everything has a cause. All of our ideas, all of our thoughts, all of our impulses have physical causes, so we ourselves have no free will. Well, I'm not going to address the Calvinists' viewpoint today, but I am going to turn Sam Harris's argument on its head and argue that causal determinism is an illusion. This is part 2. I made one video before on this subject. In this video, I'm going to give evidence from physics, and that's me. So what's this all about? What's my angle? I'm not claiming that the idea of cause and effect is wrong. This is certainly very useful in daily life. We need to know what to expect when we do something. What I am saying is that what we call cause and effect may simply be correlation between effects due to causes outside of space and time. In other words, what I'm saying is that cause and effect, in some sense, is an illusion, just like the illusion of the sun going around the Earth, that physics tells us is not the more fundamental way of looking at things. I'm saying there's a more fundamental way of looking at the situation that says that causes are outside of space and time. And I gave this example in my first video of a fishing boat coming in from the ocean after a hard day's fishing. And the fishing boat leaves a wake. The waves come from the fishing boat and break on the shore. And the point where the wave breaks appears to be moving down the shore. So I'm drawing an analogy between objects that move through time and the front of this wave that breaks on the shore. Now notice that this cause of the wave out here, this fishing boat, is not in past time. It's not before the universe, which would be back in this direction. It's coming from a completely different direction. Now you might wonder, does this all really make any difference? I'm talking about causes outside of space and time, and we have no access to outside of space and time. Well, in daily life, it probably doesn't make a difference. But then again, in daily life, does it make a difference that the sun doesn't go around the Earth, but rather the Earth goes around the sun? This different way of looking at things does change your perspective and may influence your attitude towards the world, and someday it may make a practical difference. I'll also put in that the question of free will really doesn't make any practical difference either. But people still get hot and bothered about it. We all have the experience of apparent free will, so why are we arguing about it? Well, I'll leave those questions behind and go on to my arguments. I'm going to be taking a physics point of view. And of course, we've seen that many times looking at things from a physics point of view punctures the illusions we have of things in daily life. For instance, the idea that the sun goes around the Earth. Now I'm going to start out with the concept of space-time. This is a relatively recent concept. The theory of relativity says that space and time are not separate, but can rotate into each other. Let me give a quick example of what I mean by that. Consider two observers here. One has set up his coordinates or his frame of reference so that the y direction is this way and the x direction is this way. And the other one has set up his frame of reference so that his y direction is this way and his x direction is this way. Now this purple observer sees these two blue dots lined up along the y direction. This other observer also sees them lined up, but they're not lined up along the y direction. They're lined up along some other direction between the y and x direction. These two have different y directions. Now, what Einstein discovered is that in the case where two observers are moving with respect to each other, notice these two observers are stationary, they're both standing still with respect to each other, but these two observers are moving with respect to each other, then the time direction for this purple observer becomes rotated and is no longer the time direction for this pink observer. In other words, if the purple observer sees two events that happen one after another in the same place, then he would say those two events are purely along the time direction. But this pink observer doesn't see it that way. The pink observer sees the two events. Certainly he sees one after the other, but he doesn't say they're in the same place. Okay, so a pure time direction for this observer is not a pure time direction for this observer. Similarly, a pure space direction for this person is not a pure space direction for this person. This person may see two events that he thinks are simultaneous, that happen at the same time. When this person who's moving with respect to this person sees the same two events, he says, no, they're not happening at the same time. So there's no notion of simultaneity. And that's because space directions rotate into time directions for observers that move relative to each other. This gives us a picture of space and time as a single four-dimensional continuum. And we move through this continuum as we experience time. So this invites a comparison between what we see in 3 dimensions and what goes on in 4 dimensions. In a sense, time is just one more added dimension. Now, in 3 dimensions, when we talk about interactions between objects, the interactions are always mutual. So in 4 dimensions, why should we separate between cause and effect? Here's what I mean. Think about two objects in space attracting each other by gravity. They have equal and opposite forces on each other. But you don't say this one is the cause, this one is the effect. The entire phenomenon together is inseparable. Both of these are equally caused and both of these are equally affected. However, when we talk about time, if this is the time direction, we always think of what's happening before as the cause, and this may send a beam of light that strikes this. We think of the later one as the effect, and the earlier one as the cause. So why should this be different from the case of 3 dimensions? Also in 3 dimensions, there are no forward directions and backward directions. I can move east, I can move west equally. So in 4 dimensions, why should backward time be different from forward time? Now certainly we experience moving through forward time, but is that because backward time is different from forward time? Or is it more like we're on a train that's moving in one direction, and the directions themselves are not intrinsically different, it's just the fact that we happen to be moving in this one direction. I think another way to see that cause and effect could be a result of our perspective. Think of a blank piece of paper where you draw this figure on it. You have the red line coming in, meeting the green line and bouncing back again. Now suppose you put this in a scanner. The scanner is going to scan down this way. According to the scanner, the two lines are coming closer and closer together, and there's a collision. And it seems that this collision is caused by the fact that these two lines are converging and they're going to have to meet and bump up against each other. But of course, you could have scanned from the other direction and gotten the same impression, or in fact, in this case, from any one of the side directions. So this shows that it's the perspective and not the design itself that has an intrinsic cause and effect. It's just the impression that comes when you scan in one direction. Now remember this picture I had back here of cause and effect, cause being in the past and effect being in the future. I'm going to relate this picture now to electromagnetic theory. Now I've already talked about space-time and backwards time, and I've by no means given a formal argument. My purpose is just to show you that things may not be as they appear to be intuitively, and in some way the physical structure indicates that it might be otherwise. So now I'm going to talk about electrodynamics and backwards time. Now, electrodynamics is a key theory in our daily lives. The existence of atoms and chemical reactions are all based on electrodynamics. So this is really the more important force in our lives than gravity or any other force. Now, in conventional electromagnetic theory, a charge influences its future surroundings via the forward light cone. So let me show you what that means. All right, so in this picture, I have a representation of space-time. I'm trying to show 3 dimensions. Now, I can't draw 3 space dimensions and a time dimension, so I'm drawing the time dimension up, and I'm trying to draw 2 space dimensions in perspective. And here I have a moving charge. Now, this moving charge at this instant, according to conventional electromagnetic theory, exerts influence along this cone. And each line along the side of the cone is a potential light ray. So this slope here is related to the speed of light. And this charge at this instant exerts influence on any charge that lies along this light cone in the future. Now notice, the influence only extends in forward time. There's no influence in backward time. And this is the conventional electromagnetic picture. However, there's an alternative formulation of electromagnetic theory called Wheeler-Feynman electrodynamics, where moving charges influence past and future equally. So instead of the charge reaching into the future, the charge reaches into the future and the past. Okay, so we have a cone going in both directions. So any charged particle in between is determined by both past and future. If there are charges in the past that are moving and charges in the future that are moving, there's influence on the charges in between. Okay? Now, common sense perverts the conventional description, but common sense often supports illusions like the idea that friction is a natural state of motion and that the sun rises. Okay? In physics, symmetry is always preferred. So a physicist looks at this picture of a forward and backwards cone and says, well, that's much to be preferred to this forward cone. And mathematically, the 2 pictures can be shown to be equivalent, which suggests that perhaps there is forward and backward influence from charges. Okay, I've given some hints from space-time. I've given some hints from electrodynamics. Now I'm going to talk about the nature of motion. Minimization principles are important in determining shapes of trajectories. Now, trajectory, that's just the path that a particle takes as it moves. So first, let me talk about this minimum energy principle. This is not talking about a trajectory, but it's somewhat related. If you have a cable of fixed length that is hung between point A and point B, then it ends up taking the shape that minimizes the gravitational potential energy over all possible shapes. It just means that the cable wants to hang so as much of the cable is as low as possible. So just to show a quick picture, you could even apply this to a clothesline. Suppose there's a pole here and a pole here, and you have a clothesline attached to the 2. Now the line is going to hang as low down as possible. If you hang clothes on it, then you know that the point where the clothes hangs will hang even lower. That's in order to minimize the gravitational potential energy. Things want to get as low as possible. Okay. Here's another principle called the least time principle. A light ray that travels from point A to point B always ends up taking the path that minimizes time over all possible paths from A to B. And the standard example you see of that in physics books is the lifeguard. He is standing here, and there's someone out in the water who's having trouble, and the lifeguard wants to get to the person as quickly as possible. So what he's going to do is going to angle along the beach because he runs faster than he can swim, and then he angles like that. Now he's not going to go all the way over because that would waste time. The best path is the one that kind of splits the difference and gets him most of the way by running and then the rest of the way by swimming. Now that just happens to be exactly the kind of bend in the path of a light ray. If you have two different media in which the light travels faster in this media and slower in this media, you'll see exactly this bend in the shape of the light path. So again, if you take one path on the light rays, one point on the light ray path and another point on the light rays path, the distance in between is the fastest possible way that the light ray could have gotten from here to here. Okay, one more minimization principle. It's called the least action principle. And this says the path that a particle takes from space-time point A to space-time point B minimizes the total action over all possible space-time paths from A to B. All right. So this is somewhat similar to the lifeguard picture. Schematically, with my rough drawing, here I'm taking time in this direction and space along this direction. So I'm only drawing one space direction because I'm lazy. And here's a previous space-time point, and here's a subsequent space-time point. Now the action is a quantity that you compute based on the shape of the path. There might be other particles in here and other forces which will influence the action along this path. But this path is chosen in such a way that if you do calculate the action over this path, it turns out to be the path with the least action that begins at A and ends at B. So it's called naturally the principle. Now, why am I talking about these minimization principles? Notice something very remarkable. In the minimum energy principle, the shape of the cable is determined by a process. You hang the cable and it settles down to the position of lowest gravitational energy. Now, in the least time principle, is the path determined by a process? Now remember, with the lifeguard, there was a process. The lifeguard looked out and he saw the person in trouble and he calculated the way to go that took the least time. Now, if there's some physical process that minimizes the time, then the light ray, in order to minimize, must know in advance where it's going to end up. So that seems somewhat paradoxical. In the same way, in the least action principle, if that's determined by a process, then the process must take into account both the past and the future. So it can't be a process that progresses in time because it takes the future into account. So if it is a process, it must be a process in another dimension besides time and space. All right, so here's an indication that there's something going on outside of time and space that's causing things to happen. Now, originally I wanted to make this all one video, but I don't want to make the video too long. In my next installment of Physics Reasons Against Causal Determinism, I'm going to talk about quantum mechanics. So I hope you enjoyed this and hope you'll stick around for the second video.